It is our first online lecture, and the topic of today's lecture is energy stored in a capacitor. Normally, a capacitor consists of two conducting plates which is connected to a battery, and the energy from the battery will be stored in a capacitor. To understand the whole phenomena, we have a diagram here in the next slide, and the example we have taken is the parallel plate capacitor. And what we have done is that we charge the whole parallel plate capacitor by using a battery. Now here you can see that we have a battery of potential del V. We have a capacitor consisting of two parallel plates and a switch. When we close the switch, the current will flow in the circuit. The electron will move from one plate and leaving the plate a positively charged, and from the battery the electron will move into the other plate, making it a negatively charged. The battery consists of the chemical potential energy, and it will reduce, and all the reduced energy will be stored inside the capacitors. Now consider the Q amount of charge is stored on the capacitor at the same instant, and the potential difference across the capacitor can be given by the equation del V is equal to Q over C. You know about it. And with the basic definition of the work done, what is it? When we apply the force and the body will displace. Here the body is actually the charge, the dq amount of charge, and we displace it from one plate to another plate. So the amount of work done can be given as dw is equal to del V into del Q, and we can write dw is equal to Q over C into dq. The total work done required to charge the capacitor from Q is equal to 0 to Q is equal to capital Q, which is the maximum charge which can be stored on the capacitor, can be given as W is equal to integration sign. We have the limits 0 to Q and the equation Q upon C del Q. When we integrate it, we will end up in an equation W is equal to Q square over 2C, and the work done is can be given as a potential energy U is equal to Q square over 2C, and we know that it is equal to 1 upon 2 Q over del V, and it can be converted into U is equal to half C del V square. Now finally we know that del V is equal to into D, and the capacitance in a parallel plate capacitor can be given as A epsilon naught over D. We'll put in the above equation, and we will have the potential energy is equal to half A epsilon naught over D into ED square. For energy density, which is equal to energy per unit volume, where the volume is equal to AD, we can write U is equal to UE divided by AD, and we will end up in a following equation: U is equal to half epsilon naught E square. Now this is the next topic, which is very interesting. It is capacitors with dielectric. What is dielectric? Dielectric is actually a non-conducting material, normally known as insulator. It can be a paper, wax, and rubber, and others. If we consider a parallel plate capacitor almost full without the presence of dielectric, so the amount of charge present on each plate is Q naught. The potential difference between the plates is del V naught. We can write del V naught is equal to Q naught upon C naught. The naught actually defines the absence of the dielectric. When we insert a dielectric slip between the plates, it was observed that the potential difference between the plates decreases by a factor K, which can be given as by the following equation: del V is equal to del V naught divided by K. Now here we have a capacitance, which is because we have already supposed that charge on the capacitor cannot be changed. It is Q naught. So capacitance will be given as C is equal to Q naught upon del V. This del V is in the presence of dielectric. We can put the value of it, and we will find C is equal to del Q naught del V naught divided by K, and the capacitance will be given as K Q naught del V naught, and finally we have factor K into C naught, where K is always greater than 1. So for a parallel plate capacitor, we can write the capacitance will be equal to kappa K epsilon over d, we already know that kappa always has the value greater than 1. So in the presence of the dielectric, we have some advantages and we have some limitations. What we can achieve by inserting a dielectric slip, the capacitance of the capacitor can be increased, the operating voltage also increased. It means if you are operating a capacitor between 5 to 10 volt, we can increase up to 5 to 13 volt as well. And there is another thing, which is the mechanical support, because if there is no support here, there is no glass slip, we cannot decrease the distance between the two plates because the plates will bend towards each other. So with the presence of the slip, we can prevent this one. So somehow we can also decrease the distance as much as we want. And there is some limitations that we can increase the operating voltage, but there is a limitations, because if we increase so much, there will be electrical breakdown and your whole capacitor will be destroyed. So this dielectric strength is actually the maximum voltage you can apply it in the presence of the dielectric, and this is known as dielectric strength. Here is the atomic description of the dielectric. We consider that the dielectric material is polar. It can be non-polar as well. So in the absence of any electric field, they are just randomly placed over there. So their electric field, their poles are randomly orientated. In the presence of the electric field, they are forced to maintain a proper alignment. Because of that, there is a induced electric field introduced, which always oppose the applied electric field. And due to this difference, the operating voltage, which can be determined by a voltmeter, shows some decrement. Here is your assignment. You have to write a note with the derivation as well. What will happen to an electric dipole if there is electric field present? And you have also described in your own words the atomic view of the electric. All the diagrams and all the topics normally we have discussed here, taken from the book, the Physics from Scientific Engineers by Servin and Javid.